Let's talk about exactly how oxygen and carbon dioxide come into and out of the lungs. So you know this is our alveolus in the lungs. This is the last little chamber of air where the lungs are going to interface with blood vessels, right? So this is our blood vessel down here. And oxygen is going to make its way from this alveolus. It's going to go into the blood vessel. And it's going to go from the blood vessel into a little red blood cell. This is my red blood cell here. He's headed out for the first delivery of oxygen that day. And he's going to pick up some oxygen, and it's going to get inside of the red blood cell through diffusion. That's how it gets inside. So the oxygen has made its way into the red blood cell, and where do you think it goes first? Well, this red blood cell is, we sometimes think of it as a bag of hemoglobin, right? It's got millions and millions and millions of hemoglobin proteins. So this is our hemoglobin protein. It's got 4 parts to it, and each part can bind an oxygen. So hemoglobin, I can shorten this to HB. Now oxygen is going to bump into, quite literally bump into one of these hemoglobins, and it's going to bind, let's say, right here. And initially it's kind of tricky because oxygen doesn't feel very comfortable sitting on the hemoglobin or binding to hemoglobin. But once a single oxygen is bound, a second one will come and bind as well. And then a third will find it much easier, because what's happening is that as each oxygen binds, it actually changes the conformation or shape of hemoglobin, and so each subsequent oxygen has an easier time binding, and we call that cooperativity. It has the word almost like cooperation in it. And kind of an easy way to think of cooperativity, the way I think of it, is that if you're at a dinner party, you're much more likely to sit where 2 or 3 of your friends are already sitting, if you think of this as a table with 4 chairs, rather than just sitting at a table by yourself, being the first one to sit there. So we kind of like sitting with our friends, and oxygen is kind of a friendly molecule, and so it also likes to sit where, or bind where, other oxygens have already bound. What are the 2 then major ways, based on this diagram, how I've drawn it, what are the 2 major ways that oxygen is going to be transported in the blood? One is hemoglobin binding oxygen, and we call that HbO2. Just HB for hemoglobin, O2 for oxygen. And this molecule, or this enzyme, then is not really called hemoglobin anymore. Technically, it's called oxyhemoglobin. That's the name for it. And another way that you can actually transport oxygen around is that some of this oxygen, actually I underlined it there, is dissolved, O2 is dissolved in plasma. So some of the oxygen actually just gets dissolved right into the plasma, and that's how it gets moved around. Now, the vast majority of it is actually going to be moved through binding to hemoglobin. So just a little bit is dissolved in the plasma. The majority is bound to hemoglobin. So this red blood cell goes off to do its delivery. Let's say it's delivering some oxygen out here. And there is a tissue cell. It, of course, doesn't know where it's going to go that day, but it's going to go wherever its blood flow takes it. So let's say it takes a path over to this thigh cell in your, let's say, upper thigh. So this thigh cell has been making CO2. And remember, sometimes we think of CO2 as being made, only when the muscle's been working. But you could be napping, you could be doing whatever, and this CO2 is still being made because cellular respiration is always kind of happening. So this red blood cell has moved into the capillary right by this thigh cell. And so you've got a situation like this where now some of the CO2 is going to diffuse into the red blood cell like that. And what happens once it gets down there? So let me draw out now a large version of the red blood cell, just so you get a closer view of what's going on. And we're in the thigh, and the 2 big conditions in the thigh that we have to keep in mind, one is that you have a high amount of CO2, or partial pressure of CO2, and this is dissolved in the blood. And the other is that you have a low amount of oxygen, not too much oxygen in those tissues. So let's focus on that second point. If there's not too much oxygen in the tissues, and we know that the hemoglobin is kind of constantly bumping into oxygen molecules and binding them, and they fall off and new ones bind, so it's kind of a dynamic process. Now, when there's not too much oxygen around, these oxygen molecules are going to fall off, as they kind of always do in a dynamic situation, except new ones are not going to bind because there's so little oxygen around in the area that less and less oxygen is free and is available to bump into the hemoglobin and bind to it. So you're going to literally start getting some oxygen that kind of falls off the hemoglobin simply because the partial pressure of oxygen is low. So one reason for oxygen to come into the cells is going to be a low PO2. That's one reason. So these are reasons, and I'm going to give you another one. That's why I'm writing reasons for O2 delivery. So one of them is going to be simply not having too much oxygen in that area. A second reason has to do with CO2 itself. So let's actually follow what happens once CO2 starts getting into the red blood cell. Now, this first CO2 molecule, it's going to meet up with a little water. Remember, there's a lot of water in the red blood cell. In fact, there's water all over the blood. In fact, it's made of mostly water. And so it's not too hard to imagine that a water molecule might bump into the CO2. And there's an enzyme called carbonic anhydrase. And what it does is it kind of combines the water and the CO2 into what we call H2CO3, or carbonic acid. Now, if it's an acid, try to keep in mind what acids do. Acids are going to kick off a proton. So this becomes HCO3 minus, and it kicks off a proton. And notice that now you've got bicarb and proton on this side, and this bicarb is actually going to just make its way outside. So the bicarb kind of goes outside the cell. And the proton, what it does is it meets up with one of these oxyhemoglobins. It kind of finds an oxyhemoglobin. Remember, there are millions of them around. And it literally binds to hemoglobin, and it boots off the oxygen. So it binds to hemoglobin, and oxygen falls away. So this is interesting because now this is a second reason for why oxygen gets delivered to the tissues. And that is that protons compete with oxygen for, what are they competing for? For binding with hemoglobin. So they're competing for hemoglobin. Now, I said there's another thing that happens to the carbon dioxide. So what's the other thing? Turns out that carbon dioxide actually sometimes independently seeks out oxyhemoglobin. Remember, again, there are millions of them. So it'll find one, and it'll do the same thing. It'll say, well, hey, hemoglobin, why don't you just come bind with me and get rid of that oxygen? So it also competes with oxygen. So you've got some competition from protons, some competition from carbon dioxide, and when carbon dioxide actually binds, interesting thing is that it makes a proton. So guess what happens? That proton can go and compete again by itself. It can compete with oxyhemoglobin and try to kick off another oxygen. So this system is really interesting because now you've got a few reasons why you have oxygen delivery. You've got protons competing, you've got now CO2 competing with oxygen. So you've got a couple of sources of competition, and you've got, of course, just simply the fact that there's just not too much oxygen around. So these are reasons for oxygen delivery. So at this point, you've got oxygen that's delivered to the cells, and these hemoglobin molecules, they're still in our cell, of course, inside of a red blood cell, and these hemoglobin molecules have now been bound by different things. So they're no longer bound by oxygen, so you can't really call them oxyhemoglobin anymore. Instead, they have protons on them, like this, and they might have some COO minus on them. So they might have, actually, let me do that in the original kind of orangey color. So they basically have different kind of things binding to them, and as a result, the oxygen is now gone, and our system so far looks good. But let me actually now turn it around, and let's ask the question, how do we carry carbon dioxide from the thigh back to the lung? Let me start out by actually replacing the word thigh with lung. So now our blood has traveled back to the lung, and the question is, how much carbon dioxide did it bring with it, and in what different forms did that carbon dioxide come? So we've got a couple of situations. We've got a high amount of oxygen here, and we've got a low amount of CO2. So really quite different than what was happening in the thigh. So when the blood is leaving the thigh headed back to the lung, what's it got with it? Well, it's got a few things. One is that it's got hemoglobin that is bound to carbon dioxide, right? And this is actually called carbamino hemoglobin. And then it's also got some protons that are bound to hemoglobin. So the protons themselves are attached to hemoglobin. And just keep in mind that for every proton that's attached to hemoglobin, you've also got a bicarb dissolved in the plasma, right? Because it's a 1-to-1 ratio of these things. So you've got a bunch of bicarb in the plasma as well. And I'm writing in parentheses just so we don't forget that point. And finally, what else is in the blood? We've got some CO2 that just gets dissolved right into the plasma. So this is sounding a little bit like what happened with the oxygen situation, where you had some CO2 in the plasma itself. And this is what's headed back from the thigh to the lung. So now in the lung, what happens? You've got all this stuff with you. And the first thing that happens is that you've got a lot of oxygen now in the area, right? A lot of oxygen in the tissue of the lung, and it diffuses into the cell, goes into the cell, and the oxygen is, because there's so much of it, it's going to go and try to sit in these hemoglobins. It's going to try to find its spot. And if it does, what it does in terms of equations is kind of the reverse of what happened before. Now you've got a lot of oxygen here, you've got a lot of oxygen here, and because these are reversible reactions, you basically push this entire reaction to the left. So now you've got a lot of oxygen, and it basically competes for that hemoglobin again. So remember, before, the protons actually ended up snatching hemoglobin away from oxygen, and now oxygen returns the favor. It says, well, I'm going to snatch that hemoglobin right back, and you've got this proton that's kind of left out by itself. And on this side, you've got this CO2 that's kind of left out by itself. So a couple of interesting things are happening. Let me actually make sure I keep track of them up here. So what are some reasons now? What are some reasons for CO2 delivery? How is it getting delivered back to the lungs? And the first one, probably the most obvious one, is that we said that the lungs have a low CO2 content. So simply having very little CO2 around means that whatever is there is going to diffuse into the alveolus. So you're going to get, whatever's in the red blood cell is going to diffuse in here simply because there's not a lot of CO2 around. So instead of diffusing into the red blood cell, now it's going to want to diffuse out. A second reason, though this is kind of the more interesting reason, is that you actually have oxygen. Oxygen competes with protons and CO2. So it's competing with protons and CO2 for hemoglobin. And that's what we drew in our equation down there. So what it does is it basically gets you back to the oxyhemoglobin. That's the first thing, and that's what we've already drawn there, is that we've drawn oxygen bound to hemoglobin. But it means that these little CO2s fall off. They fall off. These little protons fall off, and they're back in the side of the cell, back in the inside of the cell. So if you're CO2, you can just diffuse into the alveolus. But if you're a proton, let's say you're a proton and you just fell off of the hemoglobin because it got snatched away by oxygen, well then this little bicarb is going to come back inside. This bicarb comes back inside, and it combines with the proton, and these two form, you guessed it, H2CO3. So they kind of, remember this is reversible as well, so they kind of go back and they form H2CO3. And it turns out that you can actually go from H2CO3 over here also using carbonic anhydrase. So you can basically kind of just do this whole reaction backwards, and now you can see that you've got more CO2 formed. So by having bicarb dissolved in the blood, or in the plasma, it's kind of just staying there and kind of waiting it out. And as soon as those protons are bumped off of the hemoglobin, they go and combine with them and form the CO2. So you've got CO2 coming from here, from the bicarb. You've got CO2 coming from the carbaminohemoglobin. And you've also got the CO2 that had, remember we said that some CO2 dissolved in the plasma. So 3 different ways that CO2 is actually coming back. And once all that CO2 is in the lungs, it's going to diffuse right into the alveolus because the amount of CO2 in there is so darn low that the diffusion gradient gets it going towards the alveolus. And of these different strategies, the most important one, the one that gets us most of our carbon dioxide transportation, is this one, this middle one, where the protons are actually binding hemoglobin and all that bicarbonate is dissolved in plasma. So of the 3 different ways that carbon dioxide comes back, that's the one you should pay most particular attention to.